So the question to GaN Systems is, not sure if you can comment on this, but what is the lead time and availability of the HEY 1011?
Yeah. Okay. So the Hey 1011 is the gate drive that we use, I'll say, in the article in this evaluation board, right? The exact, I'll say, lead time. I think, I'll say, I will recommend, I'll say, that the audience who ask these questions, I'll say, get in contact, I'll say, with Heyday. And get, how say, the update of that. Sometimes I say we as a partner, how say, with Heyday here, right, realize this evaluation board and including in this article, but always good, how say, to go back, how say, to the gate drive manufacturer and get, how say, the latest update in this. It is indeed, how say, a very good, how say, gate driver with crimping clearance that is actually, say, meet for the high voltage and high power applications, right? It's a driver where you have integrate, how say, power supply inside, right? So not only, how say, galvanic isolations from input to output, but it's actually, how say, also the power supply inside. So it's a very powerful and compact, how say, gate drive with a lot of feature inside. But sorry, I cannot comment on, how say, the lead time and availability of the product itself. If interest, how say, we do have, how say, this evaluation board that is actually highlighted in the article available. You can go to our website under the reference design and click on the where to buy buttons and get redirected to, how say, our distributor and get, how say, the evaluation board for your, how say, evaluations. But yeah, lead time of the part itself, I cannot comment. Yeah, I hope that answered the questions. Thank you.
Thank you, Cam. We're ready for the next question. This question is addressed to all of you. Does the cascade structure a long-term solution for GaN transistors regarding HEMT?
Shall I address this one, Bodo? Shall I start?
Yeah, David, go ahead.
I would say yes. You can see today cascade is working very well. It's already in the market with more than one company. And if you think about it, basically you are combining all the benefits of gallium nitride that helps you to hold a very high voltage in the drift region with a very compact design, but also the benefits of a silicon gate, a silicon MOSFET gate. And if you think about it, in the cascade, the gate is made of a silicon MOSFET, which is extremely reliable. And so it has a very high margin for the gate voltage. And you can use it with any commercial gate driver that you like. So it's very compatible with existing electronics and therefore very robust solution, combining, as we said, the benefits of both GaN for the high voltage section and the benefits for the silicon MOSFET for the control section on the gate. Of course, that's our point of view, but I'll open the discussion for other opinions.
Yeah, I mean,
thank you, David.
I can comment on this as well. I mean, GaN System has actually has a EHEM, right? So they are normally off. So cascade were actually being used, say, in the DHEM, where it's actually normally on, where you actually have a cascade a low voltage MOSFET to make it behave like a normally off device, right? So, but with that, I'll say, David has a point that out, right? I say, you know, the interface of the device is actually easy with I say off-the-shelf driver, right? But if we look, I say, beyond that, it is actually a system of two devices, right? You know, so there is always, I say, a question mark, I say, regarding, I say, reliability of one device versus, I say, two devices. And the good things, what I said that, I say, with you know, do we need to cascade? I mean, GaN today is actually on silicon, right? So should that be actually leveraged, I say, the monolithic, I say, integrate and have, I say, the driver inside instead, right? In order to overcome, I say, if you will call it, I say, issues of driving the device. So that's actually, I say, a reasonable, how say, alternative. If we look at the power device, say historically speaking, right, I say the first MOSFET was actually almost like a normally on MOSFET, but it's actually how to move and improve to be a normally off. If you see in the power device today, right, I say how many say cascade device there are out there, majority are actually how say normally off. So for that reasons, I believe that it's actually how say belongs to, how say, a normally off non-cascade solutions. But that's my point of view. Yeah.
Okay. Thank you, Pham. The next question will show up momentarily. That's a question to Transphorm. Why short circuit capability is important?
Yes, that's a great question, and you see this one as a requirement that's usually asked in application for motor drives or inverters, where basically your load is external, so it's outside of your control. And you may have a situation where you have these long cables going from your power electronic system going to the load, and something might happen to these cables. Somebody may trip on them, may short them. The operator may connect them wrongly. And so it's important to be resilient to a situation of short circuit where there's a short circuit somewhere in your circuit, in your schematic. And so that's basically a situation where we need to work in synergy between the power device and the gate driver. So first of all, the power device needs to survive enough time so that the gate driver can intervene and recognize the short circuit and shut it down. And just to give you just a few numbers for you as a reference, if you take a conventional gallium nitride device that you find on the market today, and you do a short circuit test, let's say you take a 650 volt GaN device and you do short circuit at 400 volts, which means that you're turning on your gate with 400 volts on drain and source. That device, that commercial device, may survive for, let's say, 300 nanoseconds, 400 nanoseconds. And that is very short. It's a very short time. And in most cases, the gate driver doesn't have enough time to recognize the short and make the system safe. So then basically, we need to come up with a technology that increases the withstanding time of GaN devices. And it's what we have shown in our article. And I don't know if you have had a chance of looking at it. Basically, we had a technology to increase the short circuit time from very small numbers, as we said, 300 nanoseconds to 3 microseconds. And so that would give plenty of time for the gate driver to detect the fault and shut down the system. Now the key, and then I'll finish to answer, the key to that is to be able to increase the lifetime during short circuit without compromising on resistance too much. And that's the big technological challenge, to increase short circuit time without compromising around. And we are, I would say, with our technology on a good path to realize that.
Thank you, David. It's good to see that design for short circuit is coming, especially if you have motor drive. It's a critical thing, especially when motors are blocked, and then the short circuit will destroy devices. Okay, here we'll go with the next question to all of you. Will GaN diodes and vertical structure GaN FETs be available soon?
I can address some of that.
Go ahead, Michael.
From EPC, yes. The GaN technology is based on a two-dimensional electron gas. So it is inherently wants to be a lateral structure. So making it a vertical structure is, at this point in time, with the current state of the technology, not really practical. So I don't see GaN devices in the near future becoming a vertical type structure. There are some disadvantages to that, but most of them have been advantageous. You can see that in the fact that it has made it easier to integrate hundreds of transistors to make very useful devices in the lateral structure compared to a vertical structure. As for the diode, there has been some work from the Fraunhofer Institute to alter the structure of the basic GaN FET, where it will reduce the forward drop voltage of the device through its gate. But those are still experimental and they're still quite far out. At this point in time, most what you would term GaN diodes will be GaN diode emulation. There's no real structure in the GaN technology to come up with a diode structure like you're used to seeing in silicon devices.
Yeah, I can chime on a little bit on what Michael commented, and then basically I agree, right? Once we go from the lateral structure, or where the advantages is actually electron mobility, in the 2-deck, right? And with the transitions to a vertical, right? The bottleneck of electron mobility is there, and you don't have that advantages again. So then I would say that likely you will face more competitions with silicon carbide rather than their intrinsic value of GaN itself. So that's how I see it. But again, it depends on also on the substrate that we are actually going to grow the vertical GaN on, right? I don't see it in the near future commercial as well. But if we have to project it out in far out in the future, yeah, I mean GaN substrate, right? It's relatively costly right now, but never say no, or never say never, right? It is possible, but it will be not in the near future that I see. Yeah.
Thank you, Cam. Let's go to the next question. Again, to all of you, is it a chance then GaN transistors, whatever the structure, cascade or not, sustain avalanche energy as MOSFETs do? So the question is just the avalanche capability of GaN.
I may start on this one, and then in case Michael and Cam, you can chime in,
yeah,
and then discuss. So basically, if you're talking about lateral GaN devices, we, as they discussed, we don't have P-type layers yet in the body, and so the the Avalanche is, so the breakdown doesn't happen through Avalanche, but it's rather a catastrophic breakdown that happens a much higher voltage than the rating of the device. So for example, just to give you again numbers so that you understand, for a 650 volt GaN device that's rated at 650 volt, actually if you take it and you measure a breakdown on that device, you see that most likely it's not breaking until, let's say, 1200 volt or 1300 volt. So there's a huge margin, there's a huge overhead on top of your rated voltage. And basically, if you're doing a test, for example, like UIS, where it's unclamped inductive switching, you see that the energy of the inductor is going to basically charging up the capacitances of the HAMT, and that energy will slowly be discharged through the HAMT itself without breaking down. So all to say that if you have enough headroom above your rated voltage, you're able actually to withstand the same tests as conventional silicon devices, because the energy will charge up the capacitors, the voltage will rise, but it's not going to damage the device because the catastrophic breakdown is much higher than actually the energy of the inductor current being charging the capacitor of the HAMT.
I'll chime in here a little bit. First of all, GaN transistors inherently don't have an avalanche. As Davide pointed out, it is simply a voltage capability and will break down. We know this because what I'm about to tell you doesn't leave this room. We did a couple of years ago look at some avalanche type tests, and of course those failed because there is no avalanche mechanism. And that is why you will see in the data sheets there's an overvoltage spec and a time associated with that. Also, EPC is very active with reliability testing. We've released as many as 12 very detailed reliability reports. And the latest work we are doing is to investigate very detailed the overvoltage situation for the GaN FETs, in particular for synchronous rectification applications, because that is identified as where most customers are looking at some form of avalanche rating. But inherently, there is no avalanche capability for GaN FETs, and you have to mitigate that through design.
Yeah, I remember that GaN Systems had a nice article years ago in my magazine where that was clearly described, and it had about 30 to 40% extra margin and breakdown voltage necessary to make the device, the GaN device, safe. And I remember I attended a conference in the US and the ECCE years ago. It's a while, really a while ago, in the early days of GaN, and there was a group that had GaN devices at the breakdown voltage used in motor drive applications, and the breakdown voltage at that time had not a margin, a safety margin included, and all what they presented there was that they had destroyed all the devices and they needed further investigation. That was a while ago. Now we know better that we have to put the extra voltage margin to stay safe.
Yeah. I mean, it's I see this question is also like a how say a future theoretically, right? I say if it's possible, yeah, it's possible. I say if we once we go vertical, come back to the vertical, right? Then we have actually the NMP. But then again, I agree with David, right? I say, do you need the rating or not? Because I say simply the device is actually overrated, much overrated, right? So you don't need it anyway. So yeah, is it a must to have? I don't think so. Because I say it can be actually overcome already, and it's actually overcome already today. Yeah.
Okay, gentlemen, let's look to the next question. What about packaged stray inductance for a GaN transistor versus a SiC of the same package? That's a little bit comparing apples and pears, because you can do, especially I know from EPC, a device without a package, so that minimize the stray inductance to absolute minimum. And to me, it does not make sense to put that into a package to do a comparison.
I could do a comment if you want.
Yeah, go.
First of all, EPC has moved to the dark side of the force, so we are doing some devices now in package. There's been a lot of calls for that, and we've come up with some nice packages now that are very reliable, and we can get them through automotive qual, and are making our customers a lot happier. As Bodo had pointed out, it is not a good thing to compare a package of a silicon carbide device to that of a GaN device, because the packages are very different, and GaN devices are a lot more sensitive to the parasitic inductances that a package introduces. So you will see everyone on this panel here, when they design their devices, they will take a lot of care to design a package to minimize those parasitic inductances to maximize the performance of the device. You have to keep in mind that GaN devices switch fast, and they switch much, much faster than any of the other competing devices. So when you have those higher IDTs, you must reduce the inductance to reduce the voltages they generate across those inductances to avoid the negative detrimental effects. And if you go through the history of EPCs and EPC's publications and work, you see that a lot of our focus has been to address getting rid or minimizing those inductances in all aspects of GaN usage.
Yeah. So from our GaN system point of view, right? I mean, package stray inductance of GaN versus SiC. I think both are fast switching device. And with fast switching device, if you would like to unleash the performance of the device, you need a lower package inductance. They are not for fun called stray inductance, because they are not there for any help, right? I mean, if you look at silicon carbide, for example, today package in silicon packets, I call them silicon packets, right? TO247, right? Pin stray inductance is a 10-15 nano Henry, right? If you just do the math of the IDT, right, and then you see the voltage overshoot as well, and and if you don't have Kelvin connections, right? It will, and that will actually give you a negative feedback to the gate drive, right? So I mean, package inductance is very important, though you can package in silicon package, but it's really limit the nature, intrinsic performance of the device. at GaN System, we have the GaN packs, right? It's a die and copper via coming out, right? You have an 0.5 nanohenry. So it's really a package that is tailored for high performance wide bandgap, like gallium nitride, right? But it's actually also good if you package a SiC device into it, right? It's copper coming out, right? So very good thermal conductivity as well. So if you want to really maximize the performance of the wide bandgap, package is one of the first things that you have to address. And Michael, I know that Alex is not here, right? But otherwise he will actually kill everyone with the package and straight inductance.
No, he's coming around.
Okay.
All my best regards to him. And
Thank you.
so we got a very detailed explanation and answer. And we are ready to get the next question. It's addressed to GaN Systems, and that person is new to wide bandgap and have concern that fast switching with GaN is a problem for EMI. Can you share more tricks than those mentioned in the article?
Yeah, actually, this came in, somewhat back to the former questions. I don't know if it's actually the same audience that's actually addressing. EMI, right? The conductive EMI. It's about the parasitic straight current that it's running through, right? That you can actually solve with relatively with more distance, and you minimize the stray capacitance and reducing the stray current there for conductive. But how about radiate EMI? I mean, if you do a PCB layout routing with best effort, right, you're still ending up with the finite stray inductance of the package. And what you're trying to optimize with the PCB routing, right? It's actually to minimize the antenna effect, right? So at the point you ending up at the package, and if the package is having stray inductance, you start to have radiate antenna there. So want it or not, your package is actually one of the source that is actually contribute to the radiate EMI, and that's why we looking at it. And a package like a GaN packs. Sorry, I have to repeat it, but it's a great package, right? Low inductance for the performance, and switching performance, but actually also EMI. Yeah, I hope.
I think as a help, I would recommend to this people who did this question, to take a look to get that book from EPC, and I think there will be quite a bit of help designing to reduce EMI. Yeah,
I have I have an older version, but knowledge never get old.
Oh no, you're absolutely right. As you said that, I have in my private library RCA data books from the 70s when I was a student, and I have Motorola power transistor design handbooks. Fundamentals never change.
Yeah. Those are the good days.
That's nothing. I have Frederick Grover's book from 1919 on inductance calculations.
Okay. At that time, my dad was 10 years old. So it's always good to see that progress is not only done by sophisticated new things, it builds on sustainable historic rules in electricity and design. Okay, we are ready for the next. Considering lack of avalanche capability, can 650 GaN replace 650 IGBTs? And can 1.2 kilovolt GaN replace 1.2 kilovolt SiC for electric vehicle main inverters? Even the GaN can replace IGBT SiC in the main inverters. What are the advantages?
I could start with this one, and then I let
go ahead,
Michael. So saying that I'm not a full expert, as we said in Avalanche, but as for what we said before, I would say yes, and you can see that as we said, a 650 volt GaN actually has an over voltage spec, and you see a breakdown that, as we said, it is for transform point of view that I'm speaking for us, is beyond 1300 volts. So there's plenty of headroom to sustain that event. And so I would say, yes, you can replace a 650 volt IGBT with a 650 volt GaN, and we see that happening with our customers. And I would say the same thing for a 1.2 kilovolt devices. If you design a GaN device for 1.2 kilovolt, that they hover at, then of course would scale proportionately, and so then we would see a breakdown of maybe 2000 volt. And so again, you're in the same situation where you can use it to replace a silicon carbide in an inverter. And as for the advantages, I would say, so we know that GaN devices have inherently lower charge, so lower capacitances, COSS, CISS. So every time you're switching, you're actually moving less capacitance, less charge around, so you have smaller switching losses. But now also the consideration to make is that if in your system your DIDT and DVDT are actually limited by your motor, so you cannot increase DVDT too much because the motor constraints keeps it low. Still, you can actually design a device with a very small Aron because of the high theory of merit of GaN, and therefore you can limit actually the conduction losses of your switching. So for the same output charge, your GaN device would actually have a much smaller Aron than a IGBT counterpart or a silicon carbide counterpart, and therefore limit conduction losses. Is there anything else, Michael or Cam, that you'd like to
I can't speak much for the high voltage devices because we haven't really gone much into high voltage devices, but I can address some aspects on the motor drive part of it. We have done a lot of work. We've released a number of boards now addressing low voltage motor drives for BLDC, and we found a lot of surprising benefits to switching the drives from MOSFETs to GaN. Sorry, I can't speak for the IGBT or the silicon carbide devices, but there are limits on the DVDT that you can expose the motor to, but that doesn't mean the GaN FET still cannot offer anything useful or beneficial to the motor. What we have found is that the GaN transitions are much cleaner. You will have a very clean transition during your switching period, and you can significantly reduce your dead times in your PWM signals. And when you collectively add up all those little changes, they result in a much cleaner sinusoidal waveform applied to your motor. That in turn makes the motor far more efficient. We found that we can get 11% more efficiency out of the mechanics of the motor because it is no longer vibrating back and forth on the mechanical components. That is the component that causes loss. So you don't get that torque ripple loss mechanism anymore. So the GaN devices do offer benefits in motor drives, but because of the lack of avalanche, which most people are really used to, you have to mitigate them through other means.
Yeah, and I mean, again, come back to the point, right? I say, do you need avalanche, right? Is it a must, or is that becomes, how say, a nice to have because, how say, manufacturer of GaN already, how say, address that? Yeah. Advantages of, say, replacing IGBT at 650. If we talk about, how say, EV drive, right? One of the aspects that, how say, we have addressed is cosmic radiations. You have a device, it's running out there. You can run up, how say, different altitude as well. So but everyone have a mission profile to address that, right? We have tested our device, and our device, how say, showing that, how say, it is far more, how say, robust than, how say, silicon, and to some aspect also silicon carbide. I can share, how say, that the data. So if you address that to me, but not on public. Quite expensive, how to run those data, but you don't need to derating, how say, the GaN to that extensive extent compared to, how say, silicon device. So there are, how say, efficiency, how say, advantages like Michael, how say, comment, right? How say, with a lower, how say, dead time, less ripple, how say, torque ripple, right? Which actually, how say, all your, how say, power that you transfer from the battery to the motor, it's actually going to mechanical, how say, rotating the wheel and not vibrating, how say, the machines, right? So efficiency improvement there, reliability, it's actually also there as well. So there are, how say, a lot of argument why you should actually, how say, consider GaN, even for, how say, EV, right? For 1200 volt GaN versus SiC, you know, whatever, how say, it has to be, how say, a 1200 volt GaN, but use it, how say, in combinations with existing, how say, devices, right? With, like, how say, an IGBT, right? Doing free level, then you start to have, how say, efficiency that is actually really, how say, on par on inverter level. That's what I'm talking about here, on par with silicon carbide. But then, because you're using free level, you start to reducing, how say, motor winding losses, how say, eddy, that is actually associated, how say, with eddy current, right? So you start to reduce efficiency that is actually beyond the box, and really, I have to invite you to think out of the box, think it out of the, how say, inverter, right? So GaN has a lot of, how say, added value there. It's just a, how say, you know, if you have been thought about that or not.
Thank you, Cam. We can go to the next question. So the question to all is, GaN's 2D structure makes it impossible to increase voltage rating and reduce R-on in the same time. Does it mean that GaN will not be suitable for 1200 volt level higher power traction inverter design?
I'll take this one. I'll start, and then I'll open for Michael and Cam. So the question is about basically the trade-off between R-on and breakdown, and it goes also for asking whether we could make 1200 volt devices with GaN eventually. And this one goes back to the vertical versus lateral discussion. And I would say there are results coming from academia on 1200 volt devices in vertical GaN, but I can say that also in the lateral GaN, if your design is correct, if you're choosing the right materials for your device, you can actually achieve a competitive 1200 volt design. And this one is in Transphorm roadmap. We are working towards 1200 volt devices, and we can demonstrate that it's possible even with a lateral architecture if the right design is made properly and the right materials for your system, your design, your device are chosen. So definitely we see a path to 1200 volt lateral GaN, cost effective. Remember, if you go vertical GaN, right now it's extremely expensive, it's prohibitive. We have a path to 1200 volt GaN, lateral, cost effective.
Yeah.
I'll chime in there quickly. There's a company out there, Bisi, it's not on the panel today, that do 1200 volt GaN. And so it is there. There's a company that does that, number one. Number two, at EPC, we've gone to our 5th generation device. We're already working on our 6th generation device. And the big thing there has been to shrink the features down and yet still maintain the voltage capability. I think it's pretty clear from our the difference between our Gen 4 and our Gen 5 devices. We've been able to shrink the device by half, maintain on resistance, yet get a much smaller device. So the only thing that you have to give up there is you must be able to withstand the same voltage. So it is possible, and it was going to continue to move forward. So I don't see any hindrance as to getting to 1200 volt in GaN devices.
I think David has mentioned a very magical word, cost effective, right? It is going forward, back and forward, and then you have to coming back and address that. You know, it's not a problem to do a 1200 volt GaN device, but is it cost effective or not, right? People out there a lot of research already have proved higher voltage than 1200 volt as well. But again, as a supplier, we have to be responsible for our actions, right? We have to offer our customer a compelling product, right? A cost-effective product, right? Whatever it is, a 1200 volt for industrial or a 1200 volt automotive, right? But again, cost-effective is very important. We have a lot of experience doing higher voltage devices as well. But again, do research. You can do a lot of things, but have the commercial aspect into account, right? That's where things becomes distinct between market leader and market follow, right? We are extremely proud that, of course, that that we have 650 volt automotive qualified product that is in volume production. That itself already shown that it's required a lot, but so making a 1200 volt, it's easy. You can do it, but can you do it cost effectively and prove the reliability that is actually demanding from your customer?
I'll add one more
thing.
Sorry. If you look at the GaN graph of the breakdown voltage versus die area and on resistance, you'll see that GaN today is still about 300 times from its theoretical limits. That already tells you there's a long path. And remember, MOSFETs have had 40 years head start and still find ways to exceed that limit. So there's a lot of headroom still to keep going.
That's a very good point, Michael. So physically, right, specific areas on with GaN should actually enable us beyond silicon and also well beyond silicon carbide as well. But it is not commercial today. Yeah.
Thank you, gentlemen. Let's get to the next question. So to all of you, what's the major challenge to increase the voltage level of GaN? Such as from 650 to 900 to 1200. I think that was quite mentioned in the previous discussions. By simply increasing the distance between the gate and drain or other effective metals, and what the challenges to these metals come along? I think
that's a beautiful question. Bodo, please, you were saying something.
Yeah. Go ahead.
Yeah, so that's a wonderful question. I'll give you the ingredients, and then I'll let you come to the conclusion yourself. Of course, I cannot disclose technological information about our technology. But so if you think at a lateral GaN device, you have on the top, you have source, gate, and drain, and then you have a substrate at the bottom. And so when you're thinking about breakdown voltage, now you have to think, what is your weak link in your design? So what is the part that's going to break first? And so then now you go and you can see that you have a breakdown that can happen from gate to drain. And so if you want to increase voltage, you may work there to find the balance between a run and breakdown. But then also you need to take care of breakdown from drain to source, for example. And that you have to work with your materials to make sure that there's no breakdown or no leakage current happening there at the voltage that you want. And also, the last thing I'm going to say is there could be, as we all know, breakdown as shown in the literature from drain to the substrate. And depending on the configuration of that substrate and on the materials that you're implementing in your device, that breakdown between drain and substrate can be your limiting factor, or can be so high that it's actually not a limiting factor. So basically, if you want to scale from 650 volt to 900 volt to 1200 volt, you need to take care of these three things and make sure that they all, gate drain, gate source, and drain to substrate, they all exceed your rating that you're trying to achieve. If you make the design to meet all these three, you can. And we will show that we can.
Yep, I agree. You can do it. So it's not impossible, right? And yeah, process, how say that David, how say point out, right? So I mean, I can comment, but there will be, how say, the repetitions of, how say, of the answer similar to the other questions that have been answered earlier.
Yeah, I think the question's been answered already.
Thank you, gentlemen. Let's see what else we can expect on questions. Can GaNs be paralleled and achieve a good current sharing? Is there any test data available?
I can address that question, yes.
Go ahead.
We've published work going back to 2012 on paralleling GaN FETs, and very successfully. We are currently working in the background to get as many as 12 FETs in parallel and to provide solutions for that. We have a number of methods that help because there's two types of parallel. You will parallel a half bridge, for example, a building block, or a single device, and there are some subtle differences between them. But the most important thing is layout. It's all about layout and keeping symmetry in your layout, and being able to drive that from a single gate driver. The big issue there is timing. If you have mismatch in your gate signal timing to the devices, then you will have one device that will carry a lot of current during the transition that turns on first versus the others. So there's a couple of aspects you have to keep in mind. One is variation in threshold voltage between the devices. There's layout and gate driver timing. If you're using multiple gate drivers, you're going to have to tweak the timing of the signals that arrive at each of the gates to match. If you don't do that, even a balanced layout will exhibit unbalanced behavior and cause problems. But we have shown with very simple layout techniques, and we have a demo board that is out there that you can evaluate, that show extraordinarily well-balanced behavior, even with very high DVDTs or switching behavior. And we've done that for 100 volt devices, 40 volt devices, and 200 volt devices. You can do it.
Yeah. I think from our case, our applications, global applications manager, actually the same author of this article, Lucas, show already at 2018 a paper and hardware that we parallel 4 devices for 100 kilowatt applications. So yes, paralleling with GaN is not that difficult that one might think. Michael pointed out, I say, some key parameters there, right? I say the propagations delay of the gate driver, but also part-to-part variations of the propagations delay, right? Because you don't want, I say, one device, I say, to switch on earlier. Look from the threshold voltage point of view, right? How say temperature sensitivity of the GaN is actually how say less than silicon carbide. So it's actually even easier to parallel with GaN compared to silicon carbide. So I'm not sure if you are aware of it, but that's the fact.
Thank you, gentlemen. Short circuit withstand time. How long should it be?
So I'll take this one.
Yeah.
So the answer is it depends on your gate driver. So the gate driver sets the lifetime, the short circuit time needed for the device. And so the gate driver is detecting the short circuit, and there are 2 main architecture. One is the desaturation detection. The other one is the overcurrent sensing. And depending on the gate driver that you use, they are guaranteeing a certain amount of detection time, and that would determine for how long your device will have to survive under short circuit conditions. I can tell you, to give you some numbers today, if you go and look around commercial gate drivers, just nothing fancy, nothing coming from the university, but drivers that are already available for everybody to buy, you can see that they have a desaturation detection that's happening in less than 1 microsecond. I would say 900 nanoseconds, 1 microsecond time. And we tried it with our devices at Transphorm with our feature to prolong the short circuit time, and it's actually true. So we were able to have DSAT to work in 900 nanoseconds, a microsecond. So that, I would say, is a reference point around which we could design our devices. Of course, if a customer comes and needs more time because he wants to have a longer detection, or he's using a different driver, we can work with him to adjust our short circuit time accordingly.
The question is addressed to GaN Systems. You mentioned IMS in the article. With IMS, routing of layout is limited to 1 layer. Is there anything else that offer multi-layer routing like FR4 material?
Yeah, so the short answer is yes, actually. Right, limitations are IMS has a 1 layer, right. FR4, great multi-layer, then we can really do how say power signal, how say I'm not saying that how say you have to do it, but be how say careful of how say routing, how say signal and power traces close to each other, right? But yes, you can how say you can have how say in layer solutions with FR4, So you ending up have a PCB. Your top side is actually like outside of the in layer, right? It's similar to an FR4 PCB. So top side has metallization for solder the device. In between the top and the bottoms you have a in layer, for example, aluminum nitride in layer. There are out there who offer this. You can also have aluminum oxide, but
Sorry.
No problem. But of course, aluminum nitride is actually has a much better thermal conduct material, right? And then in the bottom side you also have a metal, so you can actually start to solder or sinter the device to a heatsink or cold plate. So they are available. There are some few company. If you are interested, drop me an email at cpham@GaNSystem.com. We can take that discussion further there.
Gentlemen, we had an hour of fruitful discussion. My friends in California now can enjoy the sun and the beach. And the gentleman in Munich can go
to bed.
Garden, but it's not the right time for the beer garden.
No, unfortunately not.
But in about a couple of months, I think in April, when the sun is out, you can enjoy the beer garden.
Yeah, I hope.
Gentlemen, in about 3 months, we have the next expert talk. And so long, stay healthy and stay safe. And I will say goodbye.